Okay, good morning, and welcome back to Classical Mechanics 1 at CMI. This is the 16th meeting on 18th November 2021, Thursday. Yeah, so as the rest of us join, we were talking last time about certain one-dimensional systems. Yeah, I have a question. Will it be possible to extend the deadline for the problem set 6? May I know who is asking this question? The deadline is tomorrow at 6 p.m. So please submit the answers at that on Moodle by that time. Yeah, so let us then see whether there are any other questions before we continue. If not, I will share my screen and yeah, so if there aren't any other questions at this stage, let us return to where we were. Last time we had discussed motion in one dimension subject to a conservative force described by a potential. And we were looking at the kinds of qualitative motion that can result. So this example has many of the possibilities. The potential is indicated here, x4, and the energy is indicated by this dashed line. The particle moves along the horizontal x-axis, and the potential is plotted here, the vertical axis. We observed last time that x6 is an unstable static solution where x as a function of time is equal to x6 for all t. Okay, so that is a solution of the equations of motion. And why is it a solution of the equations of motion? Can you tell me that?
So because potential, the different derivative of potential is 0.
Okay.
And so acceleration should be 0, and
yes,
the acceleration is 0 in this case.
Okay, so let me just clarify. So the equation of motion is mx double dot is equal to the force, which is given by minus v prime of x. So at the point x6, v prime of x6 is 0, and therefore x double dot is 0 at x6. So if we start the particle at time 0 at x6 with the initial velocity x dot at time 0 to be also 0. Okay, so you start the particle there with 0 initial speed, initial velocity, then then x double dot identically equal to 0 is a solution of the equation of motion. Yeah, because right-hand side would remain 0 for all time. Left-hand side is also 0, and the initial conditions are also, sorry, I didn't mean to say that. I mean, that is true, but x identically 0. I'm very sorry. I should have, both things are correct. X double dot identically 0 and x of t identically equal to x6 is a solution of the equations of motion. One second. Let me, any question about that? Why this point is a static solution? The same applies to x4, which is a local minimum of the potential. Here too, v prime of x4 is 0. And therefore, if the particle begins over there with the 0 initial velocity, then it can remain there forever. And that would be a solution of the equation of motion. Both sides of Newton's second law would be 0. Okay, so that was the idea of, yeah, there's some problem with, yeah. So any question about, I mean, in addition, we talked about other types of motion which are not necessarily static. So if the particle begins somewhere between x2 and x3, then it will oscillate back and forth with x2 and x3 as turning points. So that is oscillatory motion. Yeah. One second, I have to. Yeah. And then we talked about, this is a bounded motion because the particle's position remains bounded between x2 and x3. Whereas if the particle begins somewhere on the left here, and if the potential has gone to 0 beyond that point, yeah, then the particle can display unbounded motion. It can come in from the left, scatter against this potential, and go back out to infinity or minus infinity. Okay, so this is unbounded or untrapped motion. Yeah, whereas in this case, it was trapped trajectory. So is that terminology clear or understandable?
Yes, sir.
Okay, very good. Is that Milan?
Yes, sir.
Okay. Sure. Okay. So now I want to, now there are a few more possibilities here. In this trapped motion, the particle oscillates between x2 and x3 with a finite period. I mean, it reaches x3 in a finite amount of time, turns back, goes to x2, and so on. Now, I just, I mean, we've not done the calculations, but I want to convey the intuition, which is really very important at this stage. Yeah, on the other hand, the particle cannot be found at x equal to 0. Yeah, it's not allowed. Because at that point, given that the energy is 3, the potential at that point exceeds 3. It's a little over 4, and therefore the particle simply cannot be present at the origin. Yeah, so we say that is forbidden. It's a forbidden point. I mean, in fact, this entire region between x3 and x4 is forbidden. This entire region is forbidden. Now, between x5 and x6, again, it is an allowed region. A particle can begin somewhere here, or more precisely on the x-axis. But I will just indicate it over here. The particle, if it starts out moving to the left, it will reach x5 in a finite amount of time. Of course, it's going to slow down, momentarily come to rest at x5, turn around and continue on its way. But there is a slight complication near x6 because it is actually a local maximum of the potential. The particle cannot actually, okay, let me actually pose this as a question. What do you think the particle will do if it is moving rightwards from here? Yeah, can you speculate as to what kind of motion will result?
Sir, from
Sir,
X6.
I think it would go to X6 and stop there.
Okay, one proposal which comes from Gautam Vishwanathan is that it will go to X6 and stop there. Okay, I had another answer from somebody else, Milan Paul. I just want to collect the possibilities and then we will discuss what is. Any other suggestion?
It would like go away and away, like out of this potential curve, like it's decreasing abruptly after X6.
So you are suggesting that the particle will reach X6 and go beyond and sort of perhaps escape to infinity.
Yeah, like if it has enough energy.
Okay, no, see, we are being very clear here. The energy is the dashed line. Yeah, so we are studying motion with prescribed energy.
Okay, then if it has an initial velocity, it will go away, and if it doesn't, like, okay, it will not have an initial velocity, so it would be an unstable equilibrium. So, well,
okay, so that is Bijayan Rai is giving various possibilities. Now, okay, I am still open to further suggestions.
Hello?
Yes, please, Aryan Kusre, yes.
Yes. So at X6, the velocity is 0 and the acceleration also 0. So it might take infinite time to reach the point.
Okay, that is an interesting suggestion. And it is basically correct. Now, if the particle begins within this region, yeah, between x5 and x6, suppose over here, with some rightward directed velocity. I mean, it has to have some velocity because the energy exceeds the potential, must have a velocity. I hope everybody is comfortable with that. That velocity could be leftward or rightward directed, but suppose it is rightward directed. Yeah, the particle is going to move rightward. It's going to slow down because the potential is increasing. So the kinetic energy is going to decrease, slow down, slow down, slow down. The question is, does it reach X6 or not? And does it reach it in finite time or not? So this is the really interesting question. So Aryan has given a very interesting possibility, which is basically correct. The answer is that the particle will keep slowing down and never actually reach X6. Or in other words, if you let the time go to infinity, it will reach X6 at infinite time. It will not reach X6 in finite time. So I want to convey this intuition. Yes, please.
This kind of thing also arises in simple. Yes, this kind of thing arises in like simple pendulum, and so the particle eventually reaches point X is finite time. Like yeah, it would slow down, but then it comes like Zeno's paradox that like in one, if it takes half time to cover half, then again half, then it won't, the series won't converge. But actually, the series converges. So even if I think that if we consider the subsequence of the time that. That would eventually converge, and in finite time it will reach X6 actually.
Okay, so that is your proposal that it will reach X6 in finite time. Now I want to compare it with this. See, what you are telling me, Bijayan, is more appropriate to the region between X2 and X3. That is more like the harmonic oscillator, as you called it, or simple pendulum, as you called it. Yeah, the particle will reach X3 in finite time and will reach X2 in finite time and simply oscillate back and forth. Now, something interesting is happening in the other case, because the potential, though it is equal to the energy there, the slope of the potential has reached 0. Yeah, so something interesting happens there. And I would, though we are not doing the calculation not very difficult, but I don't want to focus on that right now. I claim, as Aryan has suggested, that the particle will keep slowing down and the time taken actually diverges. So the claim is that particle takes infinite time to reach X6. Let us, but this can be argued without any deep calculation. Suppose it reached X6 at finite time, all right, in finite time, then it will have it must have zero velocity at x6 because the energy is equal to the potential energy. It must have zero velocity. But we know that a particle that is at x6 with zero velocity simply remains at x6 with zero velocity, right? That was a static solution. We already checked that. Yeah. So on the other hand, a particle at x3 cannot remain at x3. If you start at x3 with zero velocity, sorry, it can't stay there. It has to move left because there is a non-zero force there, yeah, pushing it leftward. Whereas at x6, the force is zero, so the particle cannot move out. Yeah. Now, so these are, there are really two different solutions here. One where the particle asymptotically approaches x6 without actually getting there, and a different solution where the particle is always at x6 without moving out. So I hope I have made this plausible. I mean, the real answer lies in the equations, or in doing experiments, which can be done. Okay, but before we try again, please tell me if this is understandable or at least plausible.
Sir,
Yes, Rajdeep Ghosh, yes.
so I just want to know that if x5 was okay. No, in my mind, the way, like, it's a little weird for me to think that it will never reach x6 like infinite time.
Okay.
Just
Yeah.
saying that if the energy value was like the value of E was higher, and x6 is still a local maximum, but like x5 is still higher. In that case, it would reach, right?
Oh, absolutely. You are quite right, Rajdeep. If the energy exceeded the value at x6, so suppose the energy was so much, okay, and you started somewhere here, rightward directed, yeah, then it will reach x6 in finite time and escape further out. Okay, so that is quite right. The point, yeah. So your intuition there is correct. The point is here the energy equals the maximum of the potential, and so if you look at it more carefully, the force that the particle feels is given by the derivative of the potential, the negative derivative of the potential, right? So here, because the very derivative of the potential is approaching zero at x6, the force is becoming weaker and weaker and weaker. It has basically zero force as you approach x6. So it is not able to pull the particle there fast enough. It takes too long. On the other hand, near x5, if you're on this energy level, the force is never zero. I mean, the slope is never zero. There is a force. It will reach x5 in finite time. So I hope the difference between x5 and x6 is a little bit evident because the forces are quite different.
So, but we can actually model this kind of potential thing, like consider a simple hemispherical bowl and keep a point particle within that. And this exactly looks like that x5 and x6 are the two sides of the bowl, hemispherical bowls. So if you consider
before
the particle,
excuse me, wait. That statement itself is wrong. This is not a particle moving in a bowl. This is that is the mistake one can easily make. Yeah, this is a particle moving on this line, subject to a certain force. The analogy you have made with the bowl is more appropriate to this region. See, in the case of a bowl, it is quite a different thing. The force is actually downward. That's due to gravity. There's a constraint because of the bowl shape and so on. It is a totally different story. You are right that it will reach some point at the top and then come down and so on. That is much more relevant to this region. Though I hesitate to use that analogy at all. That is a different story altogether. A much better analogy is the following. Bijayan, do you want to say something before I give the analogy?
No, sir.
Okay, I will give you a different analogy. Here is a pen. I am treating it as a pendulum. Okay, yeah, it can oscillate like this. It reaches some kind of turning point where it comes momentarily to rest and then goes back and so on. Yeah. Suppose you make the initial energy more, all right, then it will swing through larger angles, Even more, it will swing through even larger angles. Okay. However, I claim, and this is an experiment one can actually perform, one can try to find what is the time period of this oscillation. does it grow with energy or not?
No, time period will be same. Time period will be same.
Okay, so this is the fundamental thing that is incorrect. The time period is not the same.
Be same.
Yeah.
For small oscillation,
small oscillations, it doesn't depend on the amplitude. But once the oscillations become larger, with the larger amplitude or larger energy, the time period grows. And what I wish to convey to you is that if you take a stone and tie it to a thread and have a taut string or just a rod or something like that and try to oscillate it, you will find that the time period grows. And as the oscillation becomes larger and larger, the time period will actually diverge. Of course, it is not so easy to demonstrate that experimentally with very basic equipment, but one can do careful experiments to see this. Basically, the particle will, if you give just enough energy to reach the top, it will do so only in the infinite future. So that is a much better analogy. The oscillation of a particle in a bowl with inclined sides, unfortunately, in that case, the force doesn't reach zero at any point on those sides. You really want the slope to become zero. That is very important. Yeah, of course, one can compute this time and show that it is infinite, the time to reach x6. I mean, it's just one integral. We'll do it at some point. But at least, is the statement clear?
Yes, sir.
Okay. Yeah, anybody else who would like to ask any question about this? This may be slightly counterintuitive, but okay. See, if you are another approach is to think in terms of the uniqueness of solutions of Newton's second law equation of motion. All right. The claim is that if you have specified initial conditions, then the solution is unique. If you give x of 0 and x dot of 0, then the solution is unique. Now let us look what happens here. Suppose you start at x6 with zero initial, with location x6 as initial location and initial speed as 0. Then there is only one trajectory, and that is to remain as x6 for all times. On the other hand, if you have a trajectory that is trying to approach x6, suppose it reaches it in finite time, yeah, then the trajectory would have to come to rest at x6, yeah, because there is no force there. And the velocity has also reached 0. Yeah. Then there is no chance of going back either. But then this is really a different trajectory. Two trajectories that both end up at x6. One that remains at x6 for all times, another one that reaches x6 through some other route. Yeah, this violates the uniqueness of solutions of this equation. So if one wants to think that way, it is possible to do so. These two, yes, please, Rajdeep, yes.
So could you explain the second solution to this, to the one that ends in x? Could you explain it one more time?
Okay, okay. Let me do this once again. Yeah, there are two trajectories I want you to consider. One, which is x at 0 is equal to x6 and x dot of 0 is equal to 0. That is, you start at x6 and you are there and you start there with no speed. All right. Then solution is x of t is identically equal to x6 for all times. Yeah, because it satisfies these two initial conditions. Yeah, because it's identically x6. So if you differentiate, you will get 0. It also satisfies the equation of motion, which says that x double dot or mx double dot is equal to minus v prime of x6, but that is itself 0. And if x is identically x6, its second derivative must also be 0. So equation of motion is satisfied, initial conditions are satisfied. So this is a solution. So Rajdeep, are you comfortable with this solution?
Yes, sir. This is okay. This is
okay. Very good. Now I claim that there is another solution, yeah, which starts out, and by the way, this solution, though I started it at t equal to 0, there is no harm. I can extend it somewhat backward in time. I can start it at -10 and -100 and -2000 time also. Okay, so there really is a solution where the particle is forever at x6 from the infinite past to the infinite future. Okay, are you comfortable with that kind of solution?
Yes, sir. Yes, sir. No.
Okay, great. Now, there is now another solution that others are proposing where the particle starts out somewhere here between x5 and x6 with some non-zero speed moving rightward. Yeah. And because it is slowing down, it will take some time. But the question is, does it reach x6 in finite time or not? Okay. Suppose it reaches x6 in finite time. Okay, we make this assumption. Now we will draw a contradiction, come to a contradiction. So the particle then will reach x6 in finite time. So now we are discovering a new solution. So it reaches at finite time. So let that time be called TF, some finite time. So at t equal to TF, x of TF is equal to x6. Furthermore, because the energy was exactly equal to the potential, x dot of TF is equal to 0. So are you okay with these two statements, Rajdeep?
Yes, sir. Yes,
okay. So what have we discovered now? We have now discovered a solution which started out somewhere else, moved rightwards, and eventually reached x6 at time TF. Now compare these two solutions. Solution 1 also has similar conditions. X of TF is 0, sorry, is x6, and x of TF dot is 0. Okay, because it is over there forever and ever. Is that okay?
Yes, sir.
Okay, so here we are. We have two solutions, 1 and 2, both of which have the same initial conditions at time TF. Both the same conditions at time TF, the same state at TF. However, their histories are totally different. One was over there forever. The other one came there from somewhere else. That is the sense. Yeah.
Then you're assuming that for the Newton's equations of motion have only a unique solution. Like
exactly. Yeah. Correct. So in this argument, we are assuming that the solution is unique in time. Yeah, and no, that has not been proved here. But yeah, so yes, as I said, this is based on that assumption. So it's just a different viewpoint. The proper answer is to. So I'm just giving intuition from different viewpoints. Okay, the proper answer is to compute the time it takes to reach x6. There's an integral. You have to simply show that integral diverges. That is the real answer. But I'm not writing that. Yes, please. Yes.
That I'm okay with that. The fact that we could model this as some mathematical, we could model V as some function, and then we could show that if we do the equations of motion, then that diverges.
Okay.
I just want to know that in this case, where we are claiming that the equations of motion have only a unique solution when we fix the position and velocity at a certain instant of time.
Exactly. Yes.
Is that an axiom of mechanics, or is it something that can be proven?
Oh no, it can be proven. It is not some law of mechanics. It is simply a mathematical theorem. So that can be proved in a course on differential equations. This equation has unique solutions. So I am assuming that here, or at least working under that hypothesis. Yeah. Just to give another viewpoint. Is that okay?
Yes, sir. Yes.
So the argument I have made here is based on a hypothesis that has not been proven to you just now. Very much so, and you should be skeptical about that until that is proven. Okay. Yeah. But okay. Yes. Any other question?
Yes, sir. I just wanted to ask if we could intuitively look at it as that the function v or x against time should be a c infinity smooth function, which must result in x or v not being constant for a long time. I mean, for infinite amount of time.
Wait a minute. Okay, so I didn't catch. Yeah, v is a smooth function here. Yes, I mean, in fact, in my picture, v is some polynomial. So it is c infinity, but I didn't catch the rest of it.
I mean to say it must be smooth, so there cannot exist a solution where it is a constant for infinite amount of time and non-constant, or what Bijayan was suggesting.
And suddenly starts moving after being there for a very long time.
S-
Yeah. Okay. Now, yeah, I mean, you have some intuitive idea. I mean, the question is, does Newton's equation admit such solutions or not? That is, see, we are not propose some law of physics that says that the solutions to Newton's equations must be C infinity. Yeah, we have not postulated that. So I hesitate to assume that. It is a separate question whether Newton's equation or other equations of motion admit solutions that are, I mean, somewhat differentiable, somewhat smooth, but not necessarily infinitely differentiable. Avinash, yeah, so you are making a further assumption that solutions to Newton equation are C infinity. That is a very strong assumption, which we may not want to take at this stage, unless we are able to establish that. Okay, I'll try to comment on that again at some other point. Yeah, Avinash, is that okay?
Yes, sir.
Okay. Okay, since there are many questions about this, okay, I was thinking whether, yes, please. Who is speaking? Yes.
Sir, so like to put it differently,
Shubham,
given
yes.
like yes, sir. So given the two conditions for Newton's equation,
Two initial
we can
conditions,
like use
yes.
Newton's. Yes, sir. So we can use like Newton's equation to predict the future. So we can also like use it to redirect the past. But in this second example, we cannot do that. That leads to a contradiction.
Yeah, in a sense. I mean, yeah, I mean, I would put it a bit differently, but you are right. Yes. Yeah, I mean, your enunciation of the thing was a little bit unclear to me. If you want to say it more clearly, perhaps I will follow.
Yes, sir. I was saying like using we have been given the initial conditions.
Yes.
The position and velocity, so we can use Newton's equation to predict its future motion. What will it?
Yeah.
So we should also be able to redirect the past.
Not redirect, you mean evolve it in the past, in the backward time.
Yes,
yeah.
And it should be like unique. So the second one actually contradicts that.
Correct. So yes, yeah. So to put it differently, as you have said, the backward time evolution from x equal to from t equal to tf will be non-unique, because there are two possibilities here. One is the backward time evolution simply remains at x6. The other solution proposal is that it actually moves leftwards. So that would violate the uniqueness of solutions of Newton's equations in backward time evolution. Yeah, so that is what you said. That is correct. Is that okay, Shubham?
Yes, sir.
Okay, I think that is what you were saying. Yeah. So 1 and 2 would contradict the uniqueness of solutions of the backward time evolution of Newton, and that is what I was trying to convey. Yeah. Now, okay. So since there are all these questions, I am wondering whether I should actually calculate that integral. But no, let me not do that right now. I want to leave you with this intuition for now. We will proceed with that again afterwards. But I want to do something else, which is, with all this discussion about forward, backward time, let us talk about time reversal. Okay. Okay, so what do I mean by this? Okay, so please look carefully. So Newton's equation for motion in a potential, okay, that is the equation written here, x double dot is equal to minus v prime of x. Okay, one dimension for simplicity. Yeah, this equation is time reversal invariant. Okay, what does this mean? Okay, so it can be stated mathematically, but we can also think about it physically or in terms of pictures and movies. And we will do both. Okay, so let me first make a precise statement. What do we mean when we say this equation is time reversal invariant? Okay, what this means is that if x of t is a solution, then so is x of minus t. Okay, so x of t is a solution, then so is x of minus t. What does this mean roughly? So suppose x of t is this motion, particle moves like this. Suppose you take a movie of that motion. Okay. You store that movie and play that movie backwards. You will have some motion described. The claim is that that backward played movie is also a solution of the same equation of motion. Okay, so that is what it means for Newton's equation to be time reversal invariant. Any trajectory traversed backwards is also a trajectory. Yeah, any trajectory traversed backwards is also a trajectory. Yeah, I claim that this is something our intuition already conveys to us. Yeah, let us look at an example. Yeah, we have a particle moving on a line subject to some potential. Yeah, so suppose the potential I draw here. This is the potential and this is the energy. Okay, suppose the particle started here and with some rightward directed velocity, then it will move towards the right, reach this end point, turning point, and then turn back. Okay. Yeah. Suppose you played this movie backward from some point. Yeah. Suppose you started the movie over here, then the particle will be moving leftwards. And the claim is that is also a valid solution. Particle starting here and moving leftwards is also a valid solution. Okay, that is all it means. This is nothing about going back in time or anything of that sort. It just means you take a movie of a solution, play it in reverse, forward in time, and that's also a valid motion. Any comments at this stage? Okay, let us now, so let us see why this is the case. This can be proven. So to see this, let us define a new variable called t tilde, which is minus t. Okay, then we have to rewrite the equation in terms of t tilde. All right, so first we notice that d by dt tilde is equal to minus d by dt because they differ by a sign. So the derivatives will also differ by a sign. I hope that is okay. Yeah, d by dt tilde is equal to, yeah, this is called the chain rule of differentiation or similar thing. dt by d tilde is minus 1. Okay, and therefore we have this result. Similarly, we can compute the second derivative. Yeah, in that case, you will get two minus signs, and therefore the two are equal. Yeah, so d squared by dt squared is equal to d squared by dt tilde squared. They are the same. All right, and therefore now let us look at Newton's equation, which says that the second derivative of x of t is equal to minus v prime of x of t. Okay. Now let us rewrite in terms of x tilde. The second derivative we have just observed is the same. So I can replace d squared by dt squared by d squared by dt tilde squared. By the way, if you didn't catch why this is the case, please observe that d squared by dt tilde squared is simply the square of this operation. You apply it twice. That is what we mean by the second derivative. You simply apply it twice. It's a square. And therefore, that minus sign goes away. Yeah. So that is all there is to it. Okay, so I'm now rewriting Newton's equation in terms of t tilde. Left-hand side becomes d squared by dt tilde squared. X of t is now replaced by x of minus t tilde, right? Because t was minus t tilde. All right. Right-hand side minus v prime. I missed a tilde there. V prime of x of minus x tilde of minus t tilde. Oh, I'm sorry. There is no tilde. There is only one x. X of minus t tilde, because t has been replaced with minus t tilde. All right. The prime is with respect to x, not with respect to time. So that has not changed. Okay. So we have simply substituted t tilde as minus t in Newton's equation and written a new equation. So if Newton's equation is valid, this is also valid. Any questions so far? Because time reversal can be a source of much confusion. So I want to do this carefully for you. Now let us interpret what this equation is saying. It is saying that x of minus t tilde, see the function here is x of minus t tilde, here too it is x of minus t tilde. It is saying that that function satisfies the same equation as x of t satisfied. Yeah, or as x of t tilde satisfied, because the equation which says second derivative of some function is equal to minus v prime evaluated on that function. Yeah, this is Newton's equation, and we have just discovered that x of minus t tilde satisfies the same equation as x of t tilde. Okay, are you okay with this? I will give an example where this is violated. That will be quite illuminating. So, yeah, I just make a parenthetical remark here that t tilde is just a dummy variable, and it could be renamed as t once you do this transformation. So the sum and substance of this is that this equation 73 implies that x of minus t is a trajectory if x of t was a trajectory. Okay, which in physical terms means you can take a trajectory and play it backwards in time. Play it in reverse, record it, play it in reverse, and that would also be a valid trajectory. Or in other words, a movie of a solution played backwards is also an admissible motion. Okay. Now, we sometimes say these things in a more succinct way, which is quite helpful, but I just want to mention it here. So we often indicate the effect of time reversal succinctly by writing that under t goes to minus t, x of t goes to x of minus t. I hope that is easy enough to follow. X dot of t will go to minus x dot of minus t, okay, because the d by dt is going to change sign, and therefore there is going to be a minus sign. That's what we just calculated. So this is a kind of a shorthand notation for writing out such expressions in more detail. So we will say that under time reversal, x is now evaluated at minus time. Velocity gets reversed in sign. Of course, it gets evaluated at the other time, but it also gets reversed in sign. Accelerations do not change in sign. Of course, they are evaluated at the opposite time, minus t. Yeah. I mean, if the force is a function of location, then it gets evaluated at the location at the opposite time minus t, and so also the potential. Yeah. The square of velocity is unchanged in sign. Of course, it's again evaluated at minus t. Okay. So this is a simple way of summarizing what happens under t goes to minus t. Okay. Let us use these rules to verify that Newton's second law is unchanged. Yeah, Newton's second law said that mx double dot is equal to minus v prime of x. Yeah, so under t goes to minus t, x double dot will go to x double dot. Of course, it's evaluated at minus t. I am suppressing that. The main thing is that there is no change in sign. So also with v, no change in sign. So we say that this equation is time reversal invariant. Yeah. Now let me give you an equation that is not time reversal invariant, which will make it much more clear, I hope. A force that is linear in velocities leads to a Newton equation that is not time reversal invariant. Okay, so let us look at a force which is linear in velocities. You will recognize this from your homework. Mx double dot is equal to minus gamma x dot. Okay, so suppose the force is given by minus gamma x dot. Okay, more on this in the homework, but let us just consider the equation here. Now, under time reversal, the left-hand side will not change in sign, okay, because you just argued that the second derivative does not change in sign. That is what we showed here. But the right-hand side, being linear in velocity, will reverse sign. So under time reversal, this goes to, let me rewrite it here. Mx double dot is equal to minus gamma x dot will get replaced by mx double dot is equal to plus gamma x dot. Okay, under time reversal. Okay, so that equation is not the same as the original equation. Basically, the sign of gamma has gotten reversed. So it's not the same equation. And we say that Newton's equation for a force that linear in velocity is not time reversal invariant. Okay, not time reversal invariant. Okay, what this means is that in general, if x of t is a solution of this equation, then x of minus t will not in general be a solution of the same equation. Okay, a movie of a solution played backwards is not an admissible motion in this case. I will say more about this after you do the homework. But any question about this so far?
Sir?
Yes, Shubham Kumar, yes.
Sir, so like if there's a force which is like this, and we leave a particle under that force,
yes,
and it travels some path.
Yes, yes.
If we like look backwards in time,
Yes.
so will it not like transverse that path?
Exactly. It will not traverse that path. Very right. It will not traverse that path. Absolutely.
I mean, how is it?
How does this happen? Okay, you are forcing me to give the answer to the homework, but okay, let me do so. Yeah, think carefully. What is this saying? By the way, here the current has also gone off, so I think you won't even be able to see me. Okay, it's coming back. Yeah, so okay, let's look at it this way. What is the physics of this equation? Or okay, I want to leave this equation and talk about just physics a little bit away from this, yeah, because it's unnecessarily linked to the homework. Suppose a particle is moving in this room, all right? It is subject to the air friction. Okay, so the particle, suppose it started here, and somebody gave it some little velocity, or maybe on a rough sheet, the particle is moving. Maybe a ball is rolling on a rough sheet. Someone gives it some initial velocity, it rolls a little bit and comes to rest. Okay, it slows down monotonically, maybe eventually coming to rest. Okay, so that is a valid motion, satisfies some version of Newton's equation with a force that usually would depend on velocity in this case. All right, now we have recorded this motion. Let us play it backward in time. What do we observe? A particle that is somewhere here, a ball that is here, starts speeding up and speeds up and speeds up. Okay, that is the reversed motion. Now that motion is never seen. You have never seen a ball rolling on a rough sheet speeding up. Okay, so
okay, sir, I think I got the point.
Excellent. Yeah, but do others also get that point, that there are physical motions which, when played backward, are simply not observed in nature? Any question about this?
Sir, I think
yes.
Overall, on like as a big picture, I do think I.
Okay, you think you do understand on the.
You do understand, but
yes,
I think I think I'm not fully clear on what precisely we mean by a solution to Newton's equation.
A solution to Newton's what we mean by a solution to Newton's equation, we mean a function x of t whose second derivative multiplied by mass is equal to the force at the location. That is what we mean by solution to Newton's equation.
Okay, and so the domain of this function would be all of R, like would be time extending forward to infinity and backward to infinity?
Yeah, often it is possible to extend backwards and forward in time. Yes, often it is possible to do that. Yeah, often you can. Sometimes you may restrict it for some reason or the other. But here, let us suppose that the motion began in the very far past, yeah, and it's possible to extend it forward and backward in time. That is sometimes helpful to have that viewpoint. Yeah, but please go on. Yes.
All right, sir. So that was one question I had.
Yes.
I think the other question is, so in this example of this velocity dependent force, or
yes,
the ball rolling on some rough surface.
Yes.
The equation that we want to solve is for when the force is acting opposite to the ball rolling. Like in the case of friction, it's opposing the motion.
Exactly.
And so when we reverse it, we would like, if this trajectory was time reversal invariant, we would want the speeding up trajectory to also be a solution to the case where the force is opposing the ball's motion.
Exactly. Yeah. Okay. Yeah. But sorry, when you have a force opposing motion, it doesn't speed up. Exactly. Yeah.
Yes, sir. I think now I've gotten it. Thank you, sir.
Okay. So, but anybody else is also free to, Gautam Vishwanathan excluded. Anybody else is also welcome to ask question about this. It is not clear.
So in general,
yes, Rajdeep, is it? Yes.
So if our force is conservative, then we can confidently claim that it will be invariant under time reversal, right?
Sorry, one moment. Could you repeat yourself?
Yes, I was just saying that if we knew beforehand that the force was conservative, that it was the derivative of a potential, then we could confidently claim that the equations
Absolutely.
Invariant. Okay.
Correct. A conservative force is automatically time reversal invariant. Leads to a time reversal invariant. This force that I wrote down here is unfortunately not the derivative of some potential. Yeah, for a very simple reason, because it depends on x dot. So you cannot take some function of x and differentiate in x and get a x dot from there. Yeah. So this is an example of a highly non-conservative force.
Sir.
Yes.
Sir, in the case of one-dimensional motion,
yes,
we can draw a graph, right?
Yes.
With x versus t.
Yes, you can.
So x of t will represent a solution. So when we change the t to minus t, can you say how it will be represented in the graph?
Oh, okay, sure. We can try to do that.
And how?
Yeah. Yes, certainly. So, yeah. Yeah. So suppose this is t, and I'm plotting x as a function of time. Yeah. Suppose the particle begins at t equal to 0 at some location. Yeah. At some location. And suppose it is rolling on a rough surface, so that the particle does move. Perhaps its location changes with time. Yeah, after all, it's going to move. But eventually it comes to rest. Okay. So is that plausible, that this is the trajectory of a particle?
Yes, sir.
Yeah. Now, that is one possibility. There are other possibilities. Suppose you started, but not on a rough surface, but you started somewhere. Then the particle may oscillate, for instance. Yeah, maybe there is some restoring force that makes it move up and down. Yeah, that kind of thing. Okay. So I have described two types of forward time evolution, and I have plotted both of them as a function of time, x as a function of time, the graph of position as a function of time. Okay. Now let us see what we mean by a movie of this solution played backwards in time. What we mean is we start here somewhere at some time. See, t equal to 0 is not that important. Okay, you're free to start at some other time. So you start here and play the movie backward. Okay, so let me. What will you see? You will see, as the video is being played, the particle begins somewhere. It will move. The x is going to decrease. Then it is going to increase and decrease and so on. Okay, so yeah, I'm taking this solution and plotting it backwards. Yeah, I'm just following it backwards. So that's what I'm trying to do. Start somewhere, decreases, that's this, then starts increasing, reaches a maximum, then again decreases, and so on. Okay, this is the backward play of that movie. Are you okay with that, Milan?
Okay, sir.
Okay, that is what we mean by the movie of the solution played backwards in time. Of course, you have to start it somewhere. You cannot start it here and play backward because there was nothing there to play.
So it should be t dash, right?
Yeah. So when we say t to minus t, there is some little bit of imprecision there. Yeah. Yeah. So there is some time at which you can legitimately play it backward. Okay. If there is nothing to play, then it becomes a problem. Yeah.
So then can we call it something like k minus t? Because the k will get
it may help you. Sure, you could do that. Yeah. See, what I said earlier is valid. It is correct that if x of t is a solution, then x of minus t is also a solution. But in the very specific context of the picture I am drawing here, t to minus t is not very helpful because t equal to 0 is so special. Everything started there, so I can't go back. Yeah. But yes, so Romit, you are right. I would have to start the movie at some time when it is possible to play it backwards. Yeah, otherwise there's nothing to play backwards. Is that okay, Romit?
So I think Milan started the question.
Oh, I'm sorry. Okay, Milan has. Yeah. No, this question has not been answered fully. I have not finished the story. So all I have done is now played this movie backward and drawn it here. Now we make the important observation that this is also a sensible trajectory of an oscillating particle. Yeah.
Okay, I understood.
That's it. Yeah. This is a sensible motion of an oscillating particle.
Okay.
Let us now make the contrast with what happens in the other picture.
So you can first take the graph and then simply reverse the time axis, and then you can claim that the reversed the curve that you get is also a sensible trajectory.
Exactly. That is all there is to it.
Okay.
Yeah, that is physically reasonable trajectory, which will, if you check in carefully, it will solve that equation of motion. You take its second derivative and match it with the force. Does it satisfy or not? I claim it will. On the other hand, suppose this was the kind of motion that you saw and you plotted it. Now, suppose you now plot the time reversed version of that movie. Yes, now what would happen? The particle will begin somewhere. Yeah, it will begin somewhere. And then it is going to gradually speed up and move somewhere. And that is the conundrum. That is the contradiction. I've taken the movie of this solution and played it backwards in time. What does it describe? It describes a particle that begins somewhere, moving very slowly, yeah, but then starts speeding up and speeding up. Okay? Because the slope has increased. Yeah, the slope was practically zero there. The slope has gotten more and more. And we ask ourselves the question, is this a sensible trajectory? Do we see it in nature governed by the equations that led to this motion? Answer is emphatically no. You don't see particles that start rolling slowly, then speed up and so on, unless somebody is pushing it. Yeah. So Milan, is that okay?
Yes, sir, it's okay.
Graphically?
Clear,
Okay.
sir.
Very good. Okay, so I think that was a good question, and I hope it was useful to others as well. Any other question about this? So that is our brief discussion about time reversal. You are welcome to ask any question if you want at this stage. Okay. For some strange reason, I have lost all the, or at least I seem to have lost all the annotations I made earlier. Well, I don't know how that happened. Well, so be it. Yeah, okay. So if we are comfortable with that, let me now move to a slightly different concept and a set of ideas, namely small oscillations. Okay, so I want to discuss a little bit about small oscillations. And I will begin with what is called simple harmonic motion. Okay, so the linear or simple harmonic oscillator is one of the simplest mechanical systems with 1 degree of freedom. Okay, so we will just devote a little bit of time to understanding what this is. It describes, for instance, small oscillations of a particle of mass m due to a linear restoring force, say due to a spring. Now, such a system can be modeled by a force which is proportional to the particle's displacement x from equilibrium. That's very important. X is the displacement from equilibrium with a proportionality constant, which is a negative multiple of x. Okay, so minus k times x, where k is positive. Okay, so here the positive constant k is called the force constant. And it is evident from the formula that the dimension of k is force per unit length. Okay, so you can put what F is and get the in terms of mass, length, and time. Okay, now this negative sign indicates that the force tends to restore the particle to its equilibrium position rather than push it further away. I'm going to draw a picture in a moment, but that is what it means physically, that the negative sign means that the force is directed opposite to the displacement. In other words, when the spring is compressed, the force tends to make it expand, and when the spring is stretched, the force tends to make it contract. Okay, so this is what we mean by restoring. Now, as we shall see, a linear restoring force results in oscillatory motion of the particle around the point of equilibrium. Okay, I think much of this is familiar to you, but let us just do it a little bit carefully now. The specific type of oscillatory motion that results is called harmonic motion, since it involves the sine and cosine functions of time. Okay, so that is for historical reasons called harmonic motion. Now, this is a picture that is supposed to convey what is happening. You have a spring that is attached to some support here, and there is a mass at the other end. When the spring is left to itself, the mass is at a certain location. If you compress the spring, the mass goes left, but then the force is rightward directed and the mass is pushed rightwards when you compress it. When you elongate the spring, the force is leftward directed. In both cases, it tries to restore the mass to its equilibrium location. So this is equilibrium location. Okay. Now, the force F equal to minus kx is called Hooke's law after Robert Hooke, who used it to model such motion. Okay. So Hooke was a contemporary of Newton. And Newton benefited from many ideas of Hooke. And the other way around as well. Yeah. Now, more complicated or anharmonic, so this is called harmonic motion. There is also other possibilities. There are also anharmonic forces are possible, such as a cubic restoring force. Yeah, suppose the force is not minus kx, but minus gx cubed. Okay, so again it is restoring. Yeah, the minus sign is very much there, but it is not linear in x but cubic in x. Yeah, so such things are possible. They are harder to study, but they are also physically relevant. And real springs are not purely harmonic. Okay? They are not, the restoring force is not exactly proportional to displacement. They will have also these cubic corrections and so on. So if you really want to model a real spring, you will have to include such anharmonic effects. Okay, now we have said what the force is. So we can now write Newton's second law, which says that the force is equal to mass times acceleration. In which case, the equation of motion for a particle of mass m subject to a linear restoring force leads us to the differential equation mx double dot is equal to minus kx, which you have seen in the assignment and elsewhere. So as we just said, this equation could describe oscillations of the extension x of a spring of force constant k. Yeah, so that is what I just explained. Just to make it clear, the physical system we consider is, suppose L0 is the natural or equilibrium length of a spring. Okay, so L0 is the natural length of the spring. So this is L0. Now, when it is expanded or contracted, the length of the spring is L of t. Yeah, is its length as it expands and contracts. It's a function of time. The thing we have been calling x all this while is L of t minus L0. Okay, so it's very important to bear in mind that x is not the location of the spring as such, but it's the displacement relative to equilibrium. So it is the distance, the length of the spring minus the equilibrium length. But it's important also to notice that neither the equilibrium length of the spring, namely L0, nor L of t enters the equation of motion. It is really only the difference. Yeah. So it is only the departure x from the equilibrium length that enters the equation of motion. L0 and L of t do not appear in the equation of motion. Yeah. So now the next stage is to understand the solution of this equation. So we will work towards that. Now it is conventional to define the parameter omega equal to square root of k upon m, yeah, which you have seen in previous assignments. Please tell me, what is the dimension of omega?
Time inverse.
That's right. The dimension of omega is an inverse time. That is easy enough to see. Recall that k had dimensions of force per unit length, and mass is of course, m is of course mass. And therefore, K upon M will have the dimensions M mass times acceleration for force, mass times acceleration, LT minus 2 upon length, upon mass times length. Yeah, K was force upon length. So I've written that, and then I've divided by mass. So we notice that you're left with T to the minus 2. So upon taking the square root, K upon M, we get dimensions of inverse time. So omega is a frequency, yeah, per second in SI units. Any questions so far? Okay. Now the equation of motion that began as mx double dot is equal to minus kx, we have now rewritten that as x double dot is equal to minus k over mx, which is then minus omega squared x. Okay, because that's how we defined omega. So the equation of motion now becomes x double dot is equal to minus omega squared x. Now we look at this equation and observe that this differential equation is linear in x. That is, x only appears to the first power. X squared doesn't appear. X to the power of 0 also doesn't appear. Neither does x cubed or sine x or any other such thing. Okay. So this is a very, very special type of Newton equation that happens to be linear. And in such a circumstance, it also implies that any linear combination of solutions, suppose x1 of t and x2 of t are both solutions of this equation, then you can take a linear combination with any real constants a and b, that is again a solution of this equation. Okay, because each of them will solve this equation. You can add them. Things will simply separate out, and x1 double dot will give you minus omega squared x1, and x2 double dot will give you minus omega squared x2. And so the equation for x1 plus x2 will also be satisfied, or for that matter, ax1 plus bx2. Is that okay? So if Newton's equation is linear in this fashion, then you do have a superposition principle for solutions. Okay. Any question? Okay. So we have superposition, linear superposition of solutions, but how do you find solutions? Yeah, how do we solve it? Okay. So let us begin by observing that if the force were absent, yeah, that is if the force constant was 0, k is 0, then omega is also 0, omega is square root of k upon m. Yeah, then the equation simply becomes x double dot is 0, and we know the solution. We can integrate once, we will get x dot is a constant, and integrate once again, and you will get x is equal to at plus b. Yeah, so this is how you get the general solution when there is no force. Notably, the general solution depends on two constants of integration, namely a and b. Yeah, this is generally true of second order ODEs, ordinary differential equations. Yeah, second order equations would have two constants of integration. The integration constants a and b are to be fixed using initial conditions such as the initial location and initial velocity at whatever initial time you wish, need not be 0. Okay, now let us proceed to our equation for the simple harmonic oscillator, namely x double dot is equal to minus omega squared x. Sadly, we cannot simply integrate this once because x appears here. I mean, you can integrate x double dot and get x dot, but you cannot simply integrate x. Yeah, we don't know what function x is, so we cannot, since we do not a priori know the integral of x, we cannot simply integrate this. Okay, so we need to be a little cleverer about it. Yeah. Now I am out of time, so I think I have to stop here. We will finish this story next time. But if there are any questions, I can try to address them before we stop. Yeah. So today we spoke about 3 main topics. One was motion of a particle in a conservative force, subject to conservative force in one dimension, subject to some potential, yeah, and the types of motion that result. some interesting features we discovered there. Then we talked about time reversal invariance, and time reversal non-invariance, all these concepts in the context of Newton's second law. And finally, we moved on to the simple harmonic oscillator, which we will continue next time. Okay, any other questions? Okay, so thank you for your excellent questions about time reversal, as well as about why the trajectory takes infinitely long to reach a maximum of the potential. That is also very nice discussion from many of you. Okay, so any question? If not, we will stop here. Please have a good lunch and we shall meet on next Tuesday. Thank you.
Thank you, sir.
Yes.
Thank you, sir.
Thank you. Yeah.
Thank you, sir.
Thank you.